Okay, what's up everybody? Today we'll be discussing rheological properties. Ano pong kinalaman ni Jollibee dito? Wala po. So, the term rheology refers to the science of the deformation and flow of materials. This is usually used for liquids and solids, no? So, kasama dito yung, for example, mga viscosity measurements and deformation of material during texture profiling. So, it came from the Greek rheo, which means current or stream. So, parang the idea is that, quote unquote, everything flows like a river, and that term was coined in the 1920s. So, in response to an applied force, a solid body will react with a deformation, kasi yung force was applied, and that deformation could happen in three possible ways, no? A body is considered as elastic when, upon removal of that force, the object returns to its normal size. Thus, yung rubber band, di ba? Elastic band, lastiko. Kapag nag-stretch siya and you let it go, it comes back to its regular shape. Unless you used up too much force and then it snaps and breaks. Next is plastic, which is upon removal of that stress, hindi full yung recovery niya. And lastly, yung fluids, which are those that deform continuously and do not recover. Parang ang sad ng mga description na to na pag naisip mo mga tao na under stress tapos hindi na makarecover. Anyway, that's another issue altogether. Okay, so here you can see the three types of force loadings. So one is uniaxial, whether it's a compression or pulling force. Basta on one axis siya, then it's called uniaxial. And then we also have bulk compression, which is force from all sides. One example of this is when you submerge something in water. So you are experiencing force from all sides. Although syempre sa tubig, pinakamalaki yung force na nasa taas mo. And that is of course the pressure that would crush you. Lastly, we have shear force, which is kung yung compression perpendicular siya dun sa surface, yung shear force ay parallel na, parang yung tectonic plates, or imagine if you have a stack of cards. Wait lang, props tayo ulit. Alright, yan. So we have a stack of cards here, there, and if I apply force on opposite directions, left and right, so that's my shear force, and it splits the cards in two directions. Okay. So again, uniaxial stress is when you are applying force along one axis perpendicular to the surface of one of the surfaces rather of your body. This could be a push or a pull, and it would cause a deformation on the material, and that type of deformation would depend on the material type as well. So if you've been playing with clay as a child, no, you would know this. Pag pinrest flat mo, let's say, yung isang cube of clay, it would compress and also spread sidewards. On the other hand, there are some things that you can compress to a greater degree. So that force applied is called the stress, okay, in this case. And the reaction or resulting deformation or change in length or one of the dimensions of the body is called your strain. Okay? And yung ratio ng stress over the strain na ito is one property unique to different materials. So based on Hooke's law, there is a linear relationship between this stress and strain. Prior to the loss of elasticity, if you look at this graph, it has strain on the x-axis, or the elongation or compression, and stress on the um, y-axis. So as you can see, habang tumataas yung stress force na ina-apply mo, ay nagkakaroon din ng percent deformation na proportional, and that proportionality is determined by the slope of this linear portion, which is called the modulus of elasticity E, or simply the Young's modulus. However, that linearity breaks apart when it reaches yung yield stress niya. Okay? And at that point, hindi na siya linear. So what happens here is na parang sa goma, parang may snapback na magaganap. Okay. And as you can see here, so hindi na siya linear, and then kung gagawin mo man siyang close to linear, parang nagbago na yung slope niya, no? Mas less na yung kanyang, so less na yung force na kailangan mong i-apply para makakuha ng greater amount of deformation. So I don't know how many of you are in a relationship, but stress and strain are definitely in some sort of relationship. So how do we interpret these stress-strain diagrams? So we can probably jump back and forth dun sa previous slide to try and see things for yourself. Dun sa first part sa elastic range, again, the ratio between the change in stress over the change in strain is constant, and in this area, strain is completely reversible. So the object would jump back to its original shape upon removal of that stress. On the non-elastic range, on the other hand, hindi na constant yung stress over strain mo. So as you can see, yung parts doon na hindi na mukhang linear yung quote-unquote slope, o hindi na siya line yung itsura niya. So that is the non-elastic range prior to the yield stress. So strain is not completely reversible at that point. And yung yield stress, yung pinaka-peak na nakita ninyo, yun naman actually yung sa point kung saan the peak itself, kaya siya nag-flatten out kasi the change in stress over the change in strain equals 0. Therefore, even without the additional application of stress, the straining continues, no, yung snap na nga na sinasabi natin. The maximum curvature, on the other hand, is where stress is at maximum and refers to the maximum strength of material, and the strain value at that point is the strain at maximum stress. And we also have a technical limit for plasticity, wherein the strain is equal to 0.2%. So, okay. Yeah, kumulog bigla. It's 3:51 in the morning here. So, yan, where was I? Technical limit of plasticity. Yeah, the stress for 0.2% of strain, and the strain is permanent, and for the strain that goes to 0.2% and is permanent. The rupture or breakage is when the stress shows a sudden drop. Okay, so rupture stress and strain at the point of rupture. Okay, so pwede nyo naman balikan para makita kung saan yung mga points na dinidescribe. Okay, ang food, hindi sila masyadong madrama in general, no? most food materials would have a stress strain curve na wala yung biglang breaking point. Yung nakita nyo kanina, ba kanina parang peak, snap, gano'n, no? Tapos may parang check. Ito, mag-taper downwards lang siya. So if you look at this one, for example, again, the 0.2% limit of elasticity is that point at which 0.2 yung epsilon mo. And then you have the slope, which is the straight line portion. So dyan na makukuha yung Young's modulus E mo. Okay, and then you have the point Rm, which is the highest point of stress, and then you have the rupture point B over here. Okay, so dito makikita natin yung iba't ibang values for the Young's modulus for different materials, food or otherwise. Again, how do we interpret the Young's modulus? So isipin natin to, di ba? Stress over strain siya. Okay, slope. So if the value is higher, so mas mataas yung stress dun sa strain, meaning to say you have to apply more stress, and the material would respond by a small amount of strain or deformation. On the other hand, a lower Young's modulus means you need to apply less stress to get the same amount of deformation. Okay? So take note yung orders of magnitude dito. Alright? This is, by the way, in newtons per square meter. So we have from 10 to the 6th all the way to 10 to the 9. So apparently, ice, as we know, is a brittle material. It has a very high Young's modulus. So it will not deform easily when you apply stress, but it will fracture and shatter if na-meet niya yung breaking point niya, right? For stainless steel, well, steel will deform, but it will take a lot of force to deform steel. So, take note, mas mataas yung value for steel than ice. So, I don't know sino nag-arrange nito, bakit hindi naman in order. And dry spaghetti, for example, has a Young's modulus just a few orders of magnitude lower than aluminum. And on the other hand, we can see that our soft foods, apple, gelatin, and banana, have relatively lower Young's moduli. No? So, I hope you can still hear me. Bumuhos yung ulan, malakas. So anyway, I hope you're all safe right now. So bulk modulus, on the other hand, is that modulus resulting from volume reduction upon subjection to bulk compression or loading. So sabi ko kanina, ito yung parang pag nilubog mo sa tubig yung isang bagay, it experiences pressure, or if you want, you can put a food material in your hand or piece of clay and then squeeze it. Then more or less it's experiencing force from all sides. Okay, the compressibility of matter, of course, gases are most compressible, next is liquid, and lastly, solid. Although you may say, sir, parang mas madaling mag-compress yung ibang solids. Well, that is simply because you're expelling the air out of, let's say, porous solids. Like, let's say, di ba, ang marshmallow, may hangin yun na trapped sa loob, na solid siya. Okay, so when you're simply expelling the air, you're not technically compressing the solids in the material, right? Gases and liquids have isotropic compression generally, meaning to say they will become a smaller version of themselves upon compression, retaining the same ratio of dimensions as composed to anisotropic solid compression. No? Alam niyo naman, pag naapakan niyo isang piraso ng clay, say shaped like a cube, it will not become a smaller cube, but it will flatten out differently under different dimensions, and so on, diba? Or when you squeeze it in your hand, it will not become a smaller cube or something. Anyway, so ang bulk modulus dito is yung K. So change over volume is equal to the proportionality constant times the change in pressure. So rearrange that and you have the bulk modulus to be equal to um, negative of the initial volume multiplied by change of pressure over the change in volume. Lastly, we have the shear modulus. Okay, there's tau and gamma here. Hindi ko alam kung yung tau gamma na frat ay initially mga physicists, but anyway. So again, di ba, we have shear force when you apply it to um, parallel to the surface. For example, this is the surface of your material, and then it causes some shear deformation. Okay? So parang 'di ba kapag clay na naman, no? Piti mo yung clay, slide mo siya in between your palms and then slide your palms, then the clay would experience shear deformation. Um, in this case, the shear stress tau is equal to the tangential force applied over the area where the force is being applied parallel to, and you have that same tau is equal to the shear modulus multiplied by tangent of the angle of deformation gamma. Okay, so and this gamma is measured in radians, which is a derived SI unit for angle. Okay, so we have here um, tangent gamma is equal to gamma, and tau therefore is equal to gamma times the angle of deformation. Sorry, shear modulus times the angle of deformation. See, in this example, we are given a cubic rubber eraser loaded with 10 newtons of tangential force, and with the shear modulus as stated, we are to find for the angle of deformation and the resulting elongation. Okay, so we have all our givens here needed. So you have your tau equal to F over A. So 20 mm squared is equal to 0.004 square meters. We equate this to the shear modulus multiplied by the angle of deformation in radians. Ito pong equation na ito applies only when the angle of deformation is sufficiently small. You can try it out on your calculators now. So we isolate gamma. Now you divide this term by this term to get a dimensionless quantity of 0.125 radians. But since 2 pi radians or 6.28 radians is equal to 360 degrees na angle, so 0.125 rad is 7.16 degrees na angle. So you can now get your x or your deformation. Ito yung x mo, which is equal to this length as well. The length of any side of the cube is 20 mm, so this one is 20 mm. Then opposite over adjacent tangent, so tangent gamma equals the ratio of your x and divided by 0.02 meters. So to get your x, you simply multiply tangent gamma, or in this case gamma, by the length of one side to get this x, which is 2.5 millimeters. So forgive my French if I butcher the pronunciation of this word. Poisson. Ayon sa YouTube. Okay, so the Poisson's ratio of is a ratio of the transverse elongation to axial compression. Simply put, when you compress a sample and it results in an increase in thickness, then the ratio of that amount of compression to the amount of increase in thickness is this ratio. Okay. Um, So it's simply the ratio of the change in thickness or over the change in length, and given by for the same strain applied. And this ratio is mu. Bakit siya may negative sign? Kasi habang kinocompress mo, nababawasan yung length, nadadagdagan yung thickness niya. So imagine a chicken cube, no? When you try to press a chicken cube down for whatever reason that you may have, mababawasan siya ng height pero tataba siya, so to speak. So this ratio for materials and mu for different materials can range from 0 to 5 in the realm of food, 0.5 rather. Hindi naman nagkakalayo. So ano bang implication nito? Let's say for cheddar cheese, it's on one hand, when you compress maybe a piece of cheddar cheese by 1 centimeter, the the thickness will increase by half a centimeter. On the other hand, if you compress a piece of cork, by how much hindi tataba yung cork, even a single millimeter. So one important thing with this ratio is that it allows you to correlate the three moduli, or rather compute. So if you know one of the three moduli plus this ratio, you can compute for the other two. We will not go any deeper at this point with moduli, but safe to say, knowing these will give you an idea about how the material would respond with respect to stress, and it's one part of profiling the physical properties of our materials, no? Although in reality, pagdating sa food, hindi pa very common ito, unlike texture profile analysis, which we will be discussing next.